All right. Hi, everybody. I'm Pam. I'm at NYU. I'm a graduate student with Todd Gracchus, and this project is done with our collaborators Ben Newell at University of New South Wales and Dan Bartels at U Chicago. So we're starting off with kind of a dumb question, which is like, can you pay people to make them learn better? Obviously, we know that incentives can change behavior. Human learning and decision-making is directed by the reward structure of our environment because we learn the values of objects and features around us to make decisions according to those values. And culturally, we ascribe a lot of power to financial reward specifically as it dictates our punishments for improper behavior and motivates us to get more sales or a better career or whatever. But more money doesn't always mean better thinking. Because we're ruled by incentives, but we're also limited by our capacities. Like if I told you I was going to pay you $1 million to memorize the dictionary in a week, just because the incentive is high doesn't mean you'll be able to do it. So we're interested in investigating what kinds of cognitive processes can be affected by incentive, what are the limits of how hard humans can think, or how fast they can learn. And of course, there exists a large literature on volitional human behavior and motivation. And we know many instances in which increasing financial incentives does improve performance, especially in mechanistic tasks like button pressing or counting, these kind of rote tasks. We can use financial rewards to motivate people to allot more attention or energy to the task and therefore improve their performance. However, there are certainly behaviors that show little to no improvement, even if we motivate them with financial incentives. For instance, we can encourage people to take more time considering things, but we can't necessarily make them avoid certain cognitive biases. And too much motivation can even be harmful, such as in the case of choking under pressure. So a long-term question for the field is, when does volitional effort yield positive effects on performance? And this is the big picture question, but specifically, we are interested in the domain of category learning. Great, so category learning is a widely studied and modeled behavior for which we still don't know how incentives will change it. We wanted to determine if we could improve category learning with financial incentives, and if we could, determine how existing cognitive models can be adjusted to account for this effect. So in our project, we use the classic Shepard, Hovland, and Jenkins category learning task from 1961, which has been replicated and dissected many, many times. The task relies on attending to relevant stimulus features to correctly distinguish two groups of objects. And for the same 8 stimuli, different assignments of the stimuli to groups varies the difficulty of the task, as some categorizations are easier to learn than others. For example, remembering that triangles are in group A and squares are in group B is easier than remembering a rule like triangles are in group A unless it's small and white, and then it's in group B. So Shepard, Hovland, and Jenkins describe these 6 different types of rules. And as rule type increases, the complexity increases, and both accuracy and speed of response decrease. And so we wanted to know if we could change this result by adding financial incentives to the equation. So I'll quickly walk you through the procedure subjects encountered. The stimuli were 8 cards with the Shepard, Hovland, and Jenkins stimuli on them. Subjects went through training about how the cards differed in shape, size, and color, and they were also given several examples of how the cards could be split into different groups according to different categorization rules. And subjects had to pass a comprehension check to make sure they understood everything. In our experiment, subjects undergo a learning phase of trials where they encounter a stimulus, guess its group, and get feedback as to whether they were right or wrong. For the first experiment we ran, this phase was 16 trials long, so subjects saw each stimulus twice. Then after the learning phase, they do a one-shot test where they see each stimulus once, and they report their belief of its group membership. So there's 8 questions on the test, 1 for each stimulus. And if they were answering completely at chance, we'd expect them to get 4 of them right, since there's only 2 possible answers on each test question. To explain the incentive manipulation, we told subjects that they had a bag of red and blue marbles, and at the end of the experiment, we pull one marble out at random. If that marble is blue, they earn a bonus $10. If that marble is red, they only receive the base payment for their time. And subjects were told that they had a certain number of marbles in their bag at the beginning of the experiment, and that answering more questions correctly on the test would turn some of the marbles blue. And we only wanted to reward correct answers above chance. So for each correct answer above chance, they could turn one of the marbles in their bag blue, up to a maximum of turning 4 of the marbles blue. So there were 3 between subjects incentive conditions, a low, medium, and high condition. In the low condition, there's 64 marbles in the bag. The medium condition, there's 8 marbles in the bag. High condition, there's 4 marbles in the bag. So these differed by the maximal probability of winning the bonus. And again, the number of blue marbles depends on how many answers on the test they got correct. So if a subject gets all the test questions correct and turns the maximum number of marbles blue, which is 4, this corresponds to a bonus probability of 6.25 in the low incentive condition, 50% in the medium incentive condition, and 100% in the high incentive condition. So this was the design of the first experiment we ran, and we tested all 6 categorization rule types at the 3 different incentive levels, completely between subjects. What we found was we do see a general decrease in performance as the categorization rule type increases. So this reproduces the classic Shepard-Hoblin-Jenkins result. However, there was no effective incentive on performance for any of the rule types. And again, here, performance is measured as % correct on those test questions. And here I'm just showing the results for rule 2 and 4 for experiment 1, because in the later experiments, we only tested these 2 rules. So no effect, we found no effective incentive on performance in experiment 1. Let's look at the design, see what we need to change. Like maybe I just didn't find it, I gotta do better, right? So my first thought was, okay, maybe 16 learning trials wasn't enough. They didn't get enough of a chance to like learn the associations, they didn't learn the rules. So let's double the learning phase and try it again. And this time, like I said, we only tested rule types 2 and 4 because testing and a low and a high incentive condition, because 18 conditions was too many. As you can see, just like in experiment 1 on the left, there was no positive effective incentive on performance in experiment 2. So another X. After these experiments, I wanted to try something a little different. I had this theory that the probabilistic nature of the reward was like really confusing and complicated. It's even weird for me to explain it here. And we're aware that like conveying probabilities to subjects using verbal explanations is pretty limited. And subjects, maybe they didn't understand the probabilities the way we expected them to. So in the next experiment, we used a magnitude-based incentive rather than probabilistic. For the magnitude incentive, each correct answer above chance on the test earned the subject an additional bonus ticket that was worth a fixed amount. So in the high incentive condition, subjects played for bonus tickets worth $2.50 each, so they could earn a maximum $10 bonus just like before. And in the low incentive condition, the tickets were worth 16 cents each for a total possible bonus of 64 cents, which is the expected value of maximum performance in the lowest incentive condition in the probabilistic design. And this is about 16 times less than in the high incentive condition, so it's not a small difference. Well, once again, we found no effect of incentive on performance, even when we made it less complicated and removed all of the silly language about marbles. So finally, I thought, okay, maybe the incentive needs to be within subjects to work. We've been running completely between subjects designs to avoid learning effects between blocks, but maybe that's what's stopping us from seeing an effect, because subjects don't have any relative sense of value of how much effort they should apply to the task. So in experiment 4, we had each subject play 4 games of the task, 2 with low incentive and 2 with high incentive, thinking that, okay, if they're going to put more effort into the high incentive ones, we'll see it here. And again, this looked like them playing 2 games where they earned low value bonus tickets and 2 games where they earned high value bonus tickets. Sadly, once again, there was no effective incentive on performance, even when we varied incentives within subjects. So of course, you can qualitatively see no positive effect of incentive on performance here, but we did also confirm this using Bayesian logistic regression models to predict the probability of a correct response as a function of incentive and rule type. And the posterior estimate of the effect of incentive always had its 95% highest density interval overlapping 0 in all of the models. We can also look at the response time. Maybe they're putting more effort in the high incentive condition, but we also did not find a positive effect of incentive on response time in all these task variations. And again, this was confirmed with a linear regression fit to the response time data. So even after running these 4 variations, I still had a lot more questions and ideas of things to do. So I need to squeeze more space and add some more experiments. After all of these null results, we wanted to restrict our design as much as possible to try and find an effective incentive. So we wanted to be as similar as we could to studies that we knew had found effective incentive. And our results so far suggested that rule inference and category learning weren't influenced by incentive. So we wanted to know if we remove the requirement for category learning, the rule learning, we just make them recognize the category rather than learn it, would we then see an effect of incentive on performance? So in experiment 5, subjects used a provided rule to categorize cards and determine whether there were more instances of cards in group A or cards in group B on the screen of a trial. The task would be more difficult for more complex rules, so we did expect to see an effect of rule type on performance as in the previous experiments. But the relevant rule is now provided to participants on the screen, so they don't have to rely on inference and memory. Each trial was worth a certain number of points, which in total determined their chance at winning a fixed $10 bonus. And the point values ranged from 0 to 32 across 40 trials. Finally, in this experiment, we see performance increasing with the point value of the trials. This effect is largest for rule type 4 and smaller for rule types 1 and 2. Our interpretation of this result is that for easier rules like rule types 1 and 2, marginal effort generates suitable performance such that the base rate of correct answers is higher even on the 0-point trials. And again, we fit a logistic regression model to the performance data and a separate linear model to the response time data. And the models contained subject level predictors to account for the within subject effects of incentives. In the model predicting performance, the incentive parameter estimation was greater than 0, allowing us to conclude that incentive does have a positive effect on performance. And we also found substantial effects of incentive and rule type on response time. Now, I should point out that response time in this task is meaningfully different than in the other task, because the time of response here includes reading, perception, judgment, and decision-making on each trial, rather than in the previous task where the response time was simply how long it took them to respond to a test question after they had already gone through all of the learning. So it's a tricky comparison, but it does make us consider why it is that behaviors where performance demands time and effort, those behaviors can be reliably incentivized, but behaviors that rely on internal cognitive processes like discovery or induction can't necessarily be incentivized. Yay, I finally get to put a green check mark. So we found a positive effect of incentive on performance, but only when we removed the part of the task that required inferring the rule over trials. For our final experiment, we decided to robustly replicate experiment 4, which was the category learning task with a within subjects design. But just because we wanted to see, like, maybe we just need a lot more power, maybe it's a really small effect, and we just didn't have enough power in our previous experiments. So let's do it for real this time. These recent results are not in the CogSci paper, but they say the same thing. And they verify, once again, our results of no evidence for an effect of incentive on category learning performance. And like I said, we confirmed this with some model fitting. And the only experiment in which we saw positive effect of incentive was experiment 5. In the other ones, all of those parameter estimates overlap 0. So let's conclude. In conclusion, we find no evidence that category rule discovery is modulated by incentives. However, a task that removes the requirement of rule discovery and instead demands only rule following does show sensitivity to incentives. The results suggest that perhaps there's something distinct about category rule learning that is immune to incentives. We speculate that rule discovery tasks require flexible thinking and rely on processes like working memory, which are known to have limited capacities, and those capacities can't be arbitrarily modified by incentives. In contrast, based on our results in the category recognition experiment, we think maybe more procedural forms of cognition can benefit from increased attention, effort, and practice. And our results are relevant to resource rational theories of behavior to help expand our consideration of how cognitive capacity limitations restrict true resource rationality. Certain cognitive capacities cannot be voluntarily augmented, and rule discovery may be one such type of cognition. Thank you to our collaborators, and thanks for listening.